Okay guys, welcome back to Engineers Academy. Do subscribe my channel if you haven't done it yet. Now let's solve this problem which says that the smooth uniform rod AB is supported by a ball and socket joint at A, the wall at B and the cable BC. Determine the components of reaction at A, the tension in the cable and the normal reaction at B if the rod has a mass of 20 kg. So the rod has a mass of 20 kg. So the weight must be acting at the mid length of this rod in the vertical direction. So now let's say that the weight is acting somewhere here. Let's say this is at the mid length. Let me write somewhere here. Let's say this is the weight. So this is 20 times 9.81. So 20 times 9.81. This is 196.2 the weight. And this is acting in the negative z direction, that is in the downward direction. And let's say that the weight is acting at the center of gravity G. Now at A, since we have the ball and socket joint, so we will have three support reactions. We will have AX, we will have AY, and we will have AZ. Similarly, at B, the ball is going to apply the normal force in the positive x direction, let's say, that is Bx. And the rope is applying the tension from B to C. So let's say that that tension magnitude is T. So now, first of all, we have to represent all these vectors as a Cartesian vectors, right? We have to represent all these as a Cartesian vectors. So now, first of all, we have to represent this T as a Cartesian vector, the tension in the cable from B to C. So now we know that the T vector, this will be equal to T magnitude times the unit vector from B to C, and this is equal to T magnitude, and the unit vector from B to C is the position vector from B to C divided by the magnitude of the position vector from B to C. So this is T, and the position vector from B to C can be determined if we travel from B along the x, y, and z to reach that point C. So from B we need to travel this distance. This is 1 meter distance in the negative y direction. So that is, we need to travel 1 meters in the negative j. So I will write minus 1j. So from here we will reach here, and then from this particular point we need to travel 0.5 meters in the positive z direction. So that is in the positive k. So we will write plus 0.5 k. So when we travel from B along y and then along z, we reach that point C. So from this we can say that there is no need to travel along the x direction. So this means that the I component of the position vector from B to C is 0. So then we have to find the magnitude of the position vector. So the magnitude of the position vector will be this 0 square plus 1 square plus 0.5 square under the square root using the Pythagoras theorem. So this will be 0 square plus 1 square plus 0.5 square under the square root. So this now we need to find this magnitude. This magnitude is 0 square plus 1 square plus 0.5 square. This gives us 1.118 approximately. So this magnitude is approximately 1.118, and this magnitude will be in meters, since all the units are in meters. And this is the magnitude of the position vector, and the position vector always tells us the position of a given point. So now from this we can say that T vector is equal to T, and then we have to divide this each component by this magnitude. So that will be 0 divided by 1.118 I minus 1 divided by 1.118 J plus 0.5 divided by 1.118 K. So T, and 0 divided by 1.118 is 0 I. This is minus 1 divided by 1.118. This gives us 0.894 J, and then we will have plus 0.5 divided by 1.118. So this is 0.447 K. And now if you multiply this T with each component, so we will have t as a Cartesian vector, and this will be 0 I minus 0.894 t j plus 0.447 t and k. So this is the Cartesian vector representation of the tension in that cable from B to C, and its units will be in newtons. Now this the reactions at A can be represented as a Cartesian vector, so that will be equal to A vector, and that will be AX. AX is acting in the positive I plus AY in the positive J plus AZ in the positive K. These are all the assumed direction of the ball and socket support reactions, AX, AY and AZ. Similarly, this BX, this is acting in the positive X, so I will write BX vector. So this BX vector, or we can say that B vector, let's say that the resultant at B. So since here we have the wall, so let me write this as B. So we will have B vector, and B vector have only one component, and that component is BX, since the wall can only apply the force in the perpendicular direction, that is in the positive X. So we will have plus BX I, and the J component is 0, and the K component of the B vector is 0. Similarly, the weight is acting in the downward direction, so we will write weight vector. This is weight magnitude. So weight vector is minus, since it is acting in the negative Z, so its I component is 0, its J component is 0, and it is acting in the negative K direction. So now we have represented all the forces as a Cartesian vector, and now since this uniform rod AB is in equilibrium, so we can apply the equilibrium conditions. So we can apply the summation of forces along X, that must be equals to 0. So the summation of forces along X, we have to add up all the X components. So the X component of T is 0, so we will write 0 plus the X component of A, that is AX, the X component of B is BX, and the weight is 0. So we have AX plus BX plus 0, this is equal to 0, and from this we can say that AX plus BX, this is equal to 0, and let's say this is equation 1. Similarly, if we apply the summation of forces along Y, that must be equals to 0. So now we have to add up all the Y components. So the Y component of T is this, minus 0.894 T. Then we have AY 0 and 0. So we will have plus AY, and this is equal to 0, or we can say that AY is equal to 0.894 T. So AY will be equal to, this AY will be equal to the Y component of T, since this is the Y component of T. So this is our equation 2. Once we find the T magnitude, then we will be able to find AY using this equation 2. Similarly, if we apply the summation of forces, along the Z axis, that must be equals to 0. So now we have to add up all the Z components, so the K component. So this is 0.447 plus 0.447 T. Then we have AZ plus AZ, and then we have this 0 and this minus. So we will have minus 196.2, and this is equal to 0. So now this is equation 3, and now in this equation 3 we have two unknowns. So we need to have some other equations, right? We have one unknown, 2, 3 and 4 and 5. We have 3 equations and 5 unknowns. So, and here we have 1, 2, 3 and 4 and 5. So to find these 5 unknowns, we need to have 5 equations. So now we have 3 equations and we have 5 unknowns. So we need to find out some more equations. So now if we apply the summation of moment about point A, that must be equals to 0. So that will give us some more equations. So let's say if we apply the summation of the moment about point A, that must be equals to 0. So to find the moment about point A, as we can see that the resultant A vector, or all the components of A, are passing through this point A, so they are not going to produce the moment about point A, so they will not come into our equation, this equation. So since we have three unknowns at A, so the smart method is to apply the summation of moment about point A equals to 0, so they will not come into our equation. So now we have to find the moment of this t, this bx or b vector, and the moment of this weight about point A. So using the vector approach. So now we can say that the moment arm for this t vector from point A can be a position vector from A to B. So the moment for t will be r a b, the position vector from A to B, cross t vector. So this will give us the moment of the tension in cable about point A. So this is the moment arm and this is the t Cartesian vector. Then we will write plus, then the moment for this B will be again the position vector from A to B, that will be the moment arm, or the position vector from A to B will be the moment arm for B vector. So we will write RAB cross that B vector, and then plus the moment of this weight. So then from A we need to write the position vector from A to G. The position vector from A to G will be the moment arm for this weight vector. So we can write that RAG cross the weight vector. So by adding all these, we will get some more equations to find the remaining unknowns. Now we need to find the position vector from A to B. So we will apply that same method. From A we will travel along the x, y and z to reach that point B. So I will write the position vector from A to B directly in that determinant method. So we will find the cross product using that determinant method. So to find the position vector from A to B, we need to travel from A 1.5 meters in the negative x. So 1.5 meters in the negative x means that 1.5 in the negative I. So we will reach the origin. Then from origin we need to travel 2 meters in the positive z, or in the positive k. So we will have this is I, j and k, sorry. So in the positive k we need to travel 2 meters, so this is plus 2. And then once we reach here, then we need to travel this 1 meters in the positive y, so in the positive j. So plus 1 in the positive j. So this is the position vector. So the position vector is minus 1.5 I plus 1j plus 2k. So this is the position vector. Then the t vector, we have already determined that t vector, so we will write the components of that t vector. So we will write 0, the I component is 0, the j component is minus 0.894t, and the k component is 0.447t. So this determinant will give us the moment of the tension T about point A. So then we will write plus, then I, j and k, the determinant for the second, the moment of that B vector. So again, the position vector from A to B, we will have that same components. So we will write minus 1.5 plus 1 plus 2, and B vector has only one component, that is bx, and that is along the I. So we will write bx 0 and 0. Similarly plus, and then we will write I, j and k. So now RAG, so since this weight is acting at the mid length, so this is we do not know, but if this is the length, if let's say that the length of AB is L, so then from A to G this distance is L divided by 2. So if we project the line of action of this weight onto the ground, so this vector, let me write it here, this weight is 196.2. So if we project this vector, so it will intersect with the ground, and this point will be at a distance of 0.5 meters from the point A along the y. This will, if we move it like this, right, so this vector will reach this point, and this distance from here to here, this will be equal to the half of this 1 meters, and this distance will be equal to the half of this, right? So our AG vector will be, from A we need to travel 0.75, the half of this, in the negative x, then we need to travel 0.5, the half of this, in the positive y, and then we need to travel the half of this in the positive z. So this means that our AG is 0.75 in the negative x, the half of 1.5 is 0.75, so 0.5 in the negative I, so we need to write minus 0.75. Then once we reach here, then we need to travel the half of this, that is 0.5 in the positive y, so plus 0.5, and then from here we will travel this distance, which will be the half of this 2. So the half of 2 is 1, so 1 in the positive case, so plus 1. And the weight vector is 0i, 0j, and minus. So 0, 0, and minus 196.2. So now we have three determinants, and we have to find all these determinants. This is equal to 0. Now we will find this determinant, so we will consider this and this minus this. So I will write plus I, and then we will have 1 into this minus this. So 1 into 0.447t minus 2 into minus 0.894t. This is the determinant method, right? And then this is for I. Then for j, we have to hide this, and this minus into this minus this. So, and with j, while finding the determinant, we always write minus sign. So minus j, and then for j, minus 1.5 into this minus this. So minus 1.5 into 0.447t. So this is this, and minus 0, 2 into 0 is 0, so minus 0, so we will get this. And then for k, we need to hide this and this minus 0. So for k, we will write plus k, and then minus 1.5 into this minus 0. So minus 1.5 into minus 0.894 t minus 0, since 1 into 0 is 0, so we will get this. So this is the moment of t only about point A. So the vector method is quite hectic method. We will solve this problem by using the scalar approach. I will upload that video, and then I will give the link of that video in the description of this particular video. So in order to compare both the methods, right, the other method, the scalar approach, is very simple, that saves our time. So you people need to understand both the methods, and then for a particular problem, you people need to decide that which method will be helpful. So for this problem, the scalar method is very helpful, but now for the time being, I am solving this problem using the vector approach. Next, I will upload the scalar approach of this particular method. So please do watch both the problems, both the solutions, and then compare both the solutions, and let me know in the comments if it helps for your learning or not. So this is the we have solved this determinant. Now we will solve this particular determinant for B. So now again I will hide this and this. Let me change the color, let's say. So for I will hide this and this, so this is 0 and 0. So this is 0, we will write plus I into 0. And then for j, we need to hide this and this, so minus 1.5 minus 2bx. So this is minus 1.5 into 0 is 0, minus 2bx. So minus, and with j, we need to write minus sign, so minus j minus 2bx. And then for k, we need to hide this and this is 0 minus bx. So plus k minus bx. So this is the moment due to that b vector. And then the determinant of this, so the determinant of this will be, again we need to hide this and this, so 0.5 into this minus 0. So I will write plus I and 0.5 into minus 196.2. And then for j we need to hide this and this, so this minus 0, so we will write minus j and minus 0.75 into minus 196.2 for j. So this minus 0, so this is for j. And then for k we need to hide this and this, and this is 0 minus 0, so 0k. We will write plus 0k, and the summation of all these will be equal to 0. The summation of this, this and this is equal to 0, since that that rod is in equilibrium. So now we have to add up all the I components. We will add up the summation of moment at A along the I. So we will add up all the I components, then we will add up all the J components, and we will add up all the K components. So we will have 3 more equations. So first of all, let me simplify this equation. This in the brackets, whatever is written, let me simplify this. Let me find this sum. So this is and we can add up this t, since we have this t, so we can add up these constants only. So this is 0.447 minus 2 into minus 0.894, so this gives us 2.235 t. So this brackets gives us 2.235 ti. So if we add up all the I components of the moment, so 2.235 t, then this is 0I, so we will write plus 0, and then we have this we will write plus 0.5 into minus 196.2, and this will be equal to 0. So now this is equation number 4, and now from this equation we can directly obtain this t, since we have one equation and one unknown. So now from this we can say that 2.235 t is equal to minus 0.5 into minus 196.2, and if we divide both sides of equation by 2.235, so this will cancel out and we will get t magnitude. So now t magnitude is minus 0.5 into minus 196.2 divided by 2.235. This gives us t equal to 43.873 newtons. So now we have obtained the t value, the tension in that rope from B to C. Similarly, if we apply the summation, all the components, all the J components of all the moments, right? So that will be, we will have this minus into minus, this is plus, plus 1.5 into 0.447 t, and the J component of this is minus into minus plus 2bx, and then this J component, so minus into minus is plus, and plus into minus is minus, so minus 0.75 into 196.2, and this will be equal to 0. So now in this equation we know this t, since we have determined this t. So if I insert this t value, we will be able to find bx. So let me put the t value here. So from this we can write that plus 2bx is equal to 0.75 into 196.2 minus 1.5 into 0.447 into t, and t is 43.873. I brought this term to the other side of equation, so it is positive, so it will become negative, and this term will become positive on the other side of equation. And if we divide both sides of equation by 2, so we will get that Bx magnitude. So now Bx magnitude is 0.75 into 196.2 minus 1.5 into 0.447 multiplied by 43.873 divided by 2. So Bx is 58.867 newtons. This is Bx, this is T. Similarly, if we add up all the k components, so this is the k component, this is the k component, and this is 0k component. So we will have, this is minus into minus plus, so for k plus 1.5 into 0.894 t, and t value is known, so t is 43.873. This is minus into minus plus 1.5 into 0.894 t, so 1.5 into 0.894 into t. Then we have minus Bx, so minus Bx equals to 0. So now we know Bx value, so this means that this equation will verify our T and Bx answer. If I find Bx value, this equation must give me the same Bx value if my Bx value and if my T value is correct. So now from this we can verify, since we have got 6 equations and we have 5 unknowns, we have 1, 2 and 3 and 4, and this equation was equation 5. So these 5 equations are sufficient to find those 5 unknowns. So this equation is of no use, since we know those 5 equations will give us all the 5 unknowns. So this equation will verify our answers. So now from this we can say that Bx is equal to 1.5 times 0.894 into 43.873. So let's find this. This is 1.5 into 0.894 multiplied by 43.873. This gives me 58.83, which is approximately equal to Bx. So this means that we get that same Bx value. So now once we find Bx and T using equation 1, Ax is equal to Bx. So from equation 1 we can say that Ax is equal to minus Bx. So Bx is 58.867. So now from the minus sign we can say that the assumed direction of Ax is not accurate. Ax is acting in the opposite direction. So actually Ax is acting in the negative x direction. We have assumed that Ax is acting in the positive x, but the answer tells us that Ax is acting in the opposite direction of the assumed direction. So it is acting in the negative x. Similarly, so this is from equation 1. Now from equation 2 we can find Ay. So Ay is equal to, we can say that Ay is equal to 0.894 into T. Now we know T value. T value is this, 43.873. So 0.894 into 43.873. This gives us 39.22. So Ay equals to 39.22 Newton. This is Ay. And this is Ax. And similarly to find Az, we have equation 3. So now in equation 3 we have 2 unknowns. Now T is known. So if I substitute the T value, we will be able to find Az. So let me copy this equation. And we have that third equation. So now from this we can say that Az is equal to 196.2 minus 0.447 T, and we know T value, which is 43.873. So 43.873. So this is 196.2 minus 0.447 into 43.873. This gives us Az equals to 176.589 newtons. So this is Az. So we have determined all the support reaction at A at the ball and socket. This is AX. X magnitude is 58.867, AY is 39.22, and AZ is 176.589. The wall is applying a normal force of 58.867, and the tension in the cable is 43.873. So this is the solution of this particular problem. I hope it will help you in your learning. Do subscribe Engineers Academy for the solution of such more problems from Hibbeler Statics.